Welcome back. We're looking at momentum, worksheet number 1, problem number 5. A 50 kilogram cart is moving across a frictionless floor at 2 meters per second, and a 70 kilogram boy is riding on the cart. Fun. Jumps off so that he hits the floor with 0 velocity. Interesting. Okay, cool. So let's identify that action then, and we'll do it before and after as well. So that action is he's jumping off of that thing there. And so let's do before and after picture. And you're obviously doing all of this ahead of me. You're just checking your solutions here. So beforehand, he's in some sort of cart there. He's having a grand old time. And it's moving at 2 meters per second. Great. And we know the masses of both those things. Great. And then he jumps off of this cart there. If he jumps off, maybe he shouldn't be sitting there. Maybe he should be standing there. Let's be a little bit easier. Let me not put sides on this cart here. Maybe I'll put little sides on the cart there. So now he can actually jump off. Okay. I got to get a picture in my mind of what this thing might kind of look like. So it might be like a skateboard. You know, that could be a cart. You could think about that as a cart. Those wheels are a little bit further apart. And a little cart here. And now he's going to jump off so that he comes, oh gosh, and I'm going to draw him just before he lands. Notice it's like the instant before he lands, because I don't want you to get confused about, oh, he's stopped because he put his feet on the ground. Well, we were looking at the interaction between him and the cart here, from him jumping off that cart. So I'm gonna think about it in my mind of just before he touches that ground there. So it means that his velocity is 0, not because he's stopping himself on the ground, but because he jumped off of this thing. Okay, now let's think about this in reality. If you're moving forward with that skateboard and you want to jump off but not be going as fast, are you gonna jump up, forward, backwards? I would agree. You'd jump backwards. You'd have to jump the opposite way that you're going so that you're like going faster in that opposite way, which in this case might hopefully be 0. All right, now if I jump off backwards from this thing, which way am I going to have to push this cart? Yeah, you're right. If I jump to the left, I'm going to have to push the cart to the right. So now the cart here, you think the cart's going to be moving faster or slower? And you should probably be saying, hey, this is, I don't know what it is, but it's probably going to be faster than 2 meters per second if I got to push it to the right so that I get myself going to the left a little bit more, or you could say going to the right a little bit less in this case. Okay, so I'm going to kind of think about all that ahead of time, and we'll go do these calculations here. So what change in momentum did the boy give the cart, and what was the velocity of the cart before and after the boy jumped? Well, I can do this any way I want. Let's go ahead and make a system. I'll do it the same way I've been doing most of them here, and I'll make the system both the boy and the cart. I'll make it everything that's interacting here. Now, if I do that, I know that the change in momentum of everything must be 0. The momentum of the beforehand must be equal to the momentum afterwards there. And what's the momentum before? Well, I have the momentum of the boy and cart, so I'm going to put boy and cart, and they're together, so I can kind of combine them together because they have the same velocity. And then afterwards, it's the momentum of that boy, plus we have a momentum of the cart. They're moving separately there. Well, the momentum beforehand is just the mass of the boy cart beforehand times the velocity beforehand for them, and maybe I should put boy cart on there, and the beginning velocity. Then the momentum of the boy afterwards there. Can I skip this step here and go, hey, he's not moving, so this thing's got to be 0 there. So hopefully that's okay with you. Hopefully you're seeing that by now. His velocity is 0 at the end there, so he doesn't have any momentum. Great. And then the momentum, the mass of the cart times the velocity of that cart there. Let's go see if we know any of these values here. Mass of the boy was 70 kilograms, so here's the mass of the boy. And oh, we got a pretty big cart here, so it's not like a skateboard, it's actually a really heavy cart. 50 kilograms, and they're moving at an original velocity here of 2 meters per second. Okay, cool. So that means that the mass here is just the mass of both of these things, which was 50 and 80 in this case. And they were moving at 2 meters per second. Did I remember that correctly? I think it is 2 meters per second. Yes, they're moving at 2 meters per second at the beginning. Okay, so on the left-hand side, I get a positive value. I add those two things together, I get 130 times 2, so that's on 260 meters per second. And then on the right-hand side, we have the mass of the cart there, so I have 0 plus. Mass of the cart was 50, we said, and I don't know the velocity that cart's moving at. Okay, so now, before I even calculate, let's just think about this here for a second. Well, I got 50 kilograms over here. I guess I shouldn't put the units on that, because it wasn't meters per second, it was meters per second times a kilogram, so it's kilogram meters per second. I'm just going to leave off the units for my calculations here. Now I think about this and I go, hey, the cart, we said that it should be moving to the right, and it should be moving faster. Well, think about this for a second. How did I get the 260? Well, I did the 50 plus 80 and multiplied by 2. Great. Well, now I'm going to divide by not 50 plus 80, I'm going to divide by just 50. That's going to give me something bigger, smaller, or equal to 2. Right? It's bigger because I'm dividing by a smaller number than what I just multiplied by to get the 260. So divide by 50 on both sides, and that's not a super nice number, so I'll go grab my calculator, and I get 5.2 meters per second we expect any velocity to be in of that cart. So that means, and notice that it's positive here. So that means that it's still moving to the right, and we said, oh yeah, he'd have to jump to the left there so that he slows himself down. And then it means he's got to push that cart to the right, which would make the cart go even faster, 5.2, so it's going a little bit more than double its original speed. Okay, cool. Sweet. So we just solved B there. What's the change of momentum? What change of momentum did the boy give the cart? Well, now I got to look at that a little bit differently here. Well, here we combined the boy and the cart, but let me go and do this... Let me do this a little bit separately here. I'm going to go ahead and, excuse me, I'm going to take this line here, and I'm going to expand that line, though. So I'm going to write it a little bit differently. We said that it was the boy and the cart together. I agree. But you could also separate those and just say, oh, it's just the momentum of that boy times the velocity of the boy at the beginning, plus the momentum of the cart times the velocity of the cart at the beginning. Okay. So now if I go and expand that, and so then let's put in the values. This was 80 times 2 there, and this thing was just 50 times 2. This means that I know my momentum of that cart beforehand right there, and the momentum of the boy beforehand right there. Oh, so I have the momentum of the cart beforehand right here. That's just the 50 times 2. And do I have the momentum of the cart afterwards somewhere? Oh, isn't it this thing right here? Isn't that what we just saw with this guy right here? And so then all of this is the momentum of the cart afterwards. Whoa. Oh, so I do have the momentum of the cart before and afterwards, and I know that the change in anything is just the momentum of the anything at the end minus the momentum of that anything at the beginning, and that is the change in momentum. So now I can just put in the numbers here. So I have 50 times, I already know that the velocity there is 5.2, so it's 50 times 5.2, if I can write 5.2. And then minus the original bit, which was 50 times 2. And so now I get a change in momentum of 160, and that's kilograms meters per second, as we figured out in that last problem there as well. You can go through and put in those numbers, units if you'd like. And that is the change of momentum of that thing. Now notice that this is a positive value here. Do I expect it to be positive value? That means that the cart gained momentum going to the right. Did it? Yeah. Yeah. Well, notice, well, it lost momentum then, because we can't gain or lose any momentum. As we said at the beginning, we can't gain or lose any momentum. If the cart gained momentum, that means that the boy must have lost momentum. Did he lose momentum? Lose momentum? Yeah. He was going fast at the beginning, 2 meters per second, and after he jumped off, he's going 0. So he lost all of that speed, you might say, velocity, motion, because it also depended on his mass there, or the proper way to say that is momentum. Yeah, so he was going forward with all this momentum. He jumped off to decrease his momentum. And you can't just destroy it, so he had to give it to the cart there. Yeah, and how did he do that? Well, he put a force on that thing to jump off, to change his momentum, and therefore he put a force on the cart, and it changed its momentum. That sounds like Newton's third law there. Oh, yeah. He put a force on himself. You put a force on the cart, which put a force on him, I should say. And so that force on the cart changed its motion, and that force on him changed its motion. That's Newton's third law there. Okay, cool. So this is like everything that we're talking about here. It's the same thing we've been talking about all year long, just a slightly different like version or flavor of that thing. Cool, great. That's it for this problem. Have a beautiful day.